They say that an angle is determined by rotating a ray, which is just half of a line, about its endpoint. So if I have a ray, half of a line, it has an endpoint on one end, it has an arrowhead on the other end showing that it's continuing on. So if I take that ray and I like stick a thumbtack right there in its endpoint and I revolve that upward, this is its initial side where it starts, this is its terminal side where it terminates or where it stops, and that revolution creates an angle. So an angle is determined by rotating a ray, which is half of a line, about its endpoint. The starting position of the ray is the initial side, and the position after rotation is its terminal side. The endpoint of the ray is the vertex of the angle. So this would be my vertex of my angle right here. Now, if your initial side is on the positive x-axis, your angle is said to be in standard position. It doesn't have to start there, but if it does, it's in standard position. And angles can go clockwise or counterclockwise. So if I start right here at 0 degrees and I go counterclockwise 45 degrees, then I would write that as a positive 45. Positive angles go counterclockwise. But if I start right here at 0 degrees and instead I go clockwise 315 degrees, I would write that as a negative 315. So when I go down, when I go clockwise, that is a negative angle measure. Now something that you'll notice about negative 315 and positive 45 is they both started at the same place and they both stopped at the same place. They had the same initial side and the same terminal side. When that happens, those are called coterminals. When they start and stop at the same point, they're called coterminals because they co-terminate. They start and stop at the same point. So a fast, easy way that you can find coterminals is just to add or subtract 360. Like if I took negative 315 and I added 360, I'd get 45. If I took 45 and I subtracted 360, I'd get negative 315. So if they give me an angle, like let's say they give me 45 degrees and they say find a couple of coterminals for that, all I would have to do is just add and subtract 360. So if I added 360, I'd get 405. If I subtracted 360, I'd get negative 315. And I can keep adding and subtracting as many times as I want to. Every single one of those answers that I get is going to be a coterminal. They are all going to start and stop at the exact same place. So it's almost like having multiple names for the same angle. And you can see that some of them are a whole lot easier to work with than others. So when we're working with trigonometry, if they give me an angle name that I'm not crazy about, like maybe they give me 405 degrees or they give me a negative 315 degrees, and I look at that and go, surely there is a better name for this angle. I could use coterminals to come up with several different names, and I might find one that I like a whole lot better, that's a whole lot easier to work with, like 45. So that when I went to draw that, I could draw that angle starting and stopping at the same place as all of its coterminals. All right, so over on page 285, they talk to us about something called radian measure. You know how we can measure length either using the English system of measure or the metric system of measure? Like if I wanted to measure the length of the classroom, I could use a yardstick or I could use a meter stick, right? Same thing is true when we're working with angles. You can measure angles with degrees, which you traditionally have done all of your life, but you also can measure angles with radians, which is what we use in upper level mathematics. In AP Calculus, we work almost entirely in radians. We very seldom use degrees. And as we work through third quarter in trigonometry, we will work more and more and more with radians and less with degrees. So let's talk about what a radian is then. The definition that they give me here, it says to define a radian, you're going to need to use the central angle of a circle. What we mean by a central angle, that's a bold print term on top of 285. A central angle is one whose vertex is the center of the circle. So here's my central angle right here because its vertex is right there on the center of the circle. So the definition of a radian on 285 says 1 radian is the measure of a central angle, like we've got here, theta, that intercepts an arc S equal in length to the radius R of the circle. So let's say that I had a radius that was 4 inches long. If I came over here and I measured an arc length that was also 4 inches long, and I made my terminal side stop where that arc length was 4 inches long, then that central angle right there would be 1 radian. When my radius is equal in length to my arc length, then that central angle will be 1 radian. So that's its formal definition. Practically, it'd be nice if I kind of had like a conversion formula. Like, it helps me to know how many feet are in a meter, like to have a way to kind of go back and forth between the two. So same story here. I could say that 1 radian is approximately 57 degrees. So if I'm looking at a circle, I know there are 360 degrees in one revolution of a circle. So if I look at that and I say, okay, if I go up about 57 degrees, there's 1 radian. Go about 57 more, there's 2. About 57 more, there's 3. 57 more, there's 4. 57 more, there's 5. 57 more, there's 6. And then I'm still going to need a little more. That kind of looks like maybe about 1/4 of a radian. So about 6 1/4 radians to go all the way around the circle. That takes me 360 degrees. To be precise, 360 degrees is equal to 2 pi radians. Now, if we approximate pi as 3.14, that would be 6.2 radians. Remember we said about 6 1/4? That makes sense, 6.28. So 360 degrees is 2 pi radians. Now, from that, we could get a few other formulas, like divide both sides of that by 2, and we'll get 180 degrees as pi radians. Divide both sides of that by 2, and we'll get 90 degrees as pi over 2 radians. Divide both sides of that by 2, and we'll get 45 degrees as pi over 4. We could go all day long, right? Multiply it by 3, divide it by 2, multiply it by 2/3. You know, whatever you want, we could come up with all kinds of equivalencies to work with here. So if I'm thinking about the quadrants that I typically work with, we have 0, 90, 180, 270, and 360 is kind of like the boundary markers that break up our quadrants. So let's think about what that would be in radians. We said that 90 degrees was the same thing as pi over 2. So right up here where we have 90 degrees, I could put pi over 2. We said that 180 was the same thing as pi. So over here where I have 180, I'll put pi. We didn't give an equivalency for 270, but we could, and here's one way of seeing it. If this is 90 degrees, 1 pi over 2, go 90 more, that'd be another pi over 2, that'd be 2 pi over 2, that's reduced into pi. Go 90 more, that'd be another pi over 2, that'd be 3 pi over 2, that makes sense, we can see why that is. And then if I come over here, remember that we had said that 2 pi was equal to 360, so where we have 360, we have 2 pi. I also could give decimal equivalents for those. If this is pi divided by 2, if I approximate pi as 3.14, 3.14 divided by 2 would give me 1.57. So this is approximately 1.57 radians right here. And that makes sense if I come back over here, because if this is 1 radian and this is 2 radians, yeah, that looks about halfway in between. That makes sense why that would be about 1.5 radians, so 1.57. Over here, pi is 3.14, and so you can see, yeah, that's a little bit past the 3 radians. Down here, if I do 3 times 3.14 and divide it by 2, I'll get 4.71. And then over here, if I do 2 times 3.14, I'll get 6.28. Now, here's how this little circle can help me. Because on the homework, they're going to say, in what quadrant is 4 radians? I don't know. Okay, well, I could look at this and say, well, if 3.14 radians is right here and 4.71 radians is right here, then 4 radians must be in the 3rd quadrant. Or they might ask me to sketch the graph of 2.5 radians. Okay, well, if this is 2 radians right here and this is 3 radians right here, then about halfway in between it'd be about right there. So 2.5. So we can use these two little charts here to help us while we're getting accustomed to these radian measures. All right, so example number 1. For example number 1, on page 286, they asked me to graph 13 pi over 6, and then they also asked me to find a couple of coterminals for it. Now, remember we talked about back here when we were working with 45 and 405 and negative 315, they were all coterminals, they would all generate the same graph. we said that 45 is a whole lot easier to work with than those other two. If you're going to have to graph this thing, go ahead and get the coterminals first. They said sketch the graph and find coterminals. Find the coterminals first because you might find one that's a whole lot easier to graph than the 13 pi over 6, right? Okay, so we said to find coterminals when we were working in degrees that we would just add or subtract 360. What's the equivalent in radians for 360 degrees? 2 pi. So if I want to find coterminals in radians, I'm just going to add or subtract 2 pi. So if to find coterminals in degrees, I added or subtracted 360, and the equivalent of 360 is 2 pi, then to find coterminals in radians, I'm just going to add or subtract 2 pi. So if they give me 13 pi over 6 and I want to find a couple of coterminals, I'm just going to add and subtract 2 pi. Now, if I add 2 pi, I need a common denominator, right? This is 2 pi over 1, and this has a denominator of 6. So let's get a common denominator of 6. That means that I'll multiply 2 pi over 1 by 6 over 6. So 2 pi times 6 is 12 pi, and 1 times 6 is 6. And now I've got a common denominator that I can combine. So, of course, with fractions, we combine the numerators, but we keep the denominator the same. So 25 pi over 6 would be a coterminal for 13 pi over 6. Not really seeing how that helped me. That kind of looks worse than the one I started with. Okay, well, let's subtract 2 pi. So if I take 13 pi over 6 and subtract 2 pi, that's another way to find a coterminal. Again, I need a common denominator because that's 2 pi over 1. So let's multiply top and bottom by 6. That'd be 12 pi over 6. So when I subtract, I get 1 pi over 6. Hey, that looks better, right? If I have a choice of graphing 13 pi over 6, 25 pi over 6, or 1 pi over 6, I'm kind of liking the 1 pi over 6. And remember that it doesn't matter which one I graph. If they're coterminals, they're all going to start and stop at the same point. So I'm good. All right, so how do I graph 1 pi over 6? Well, I have a couple of options. I could say, all right, I know that this is pi over 2. We've already identified that. And we said that 45 was pi over 4, so this would be pi over 4 right here. So if I took pi and divided it by 6, that'd be a little bit less than if I took pi and divided it by 4. So, okay, I know it's going to be a little bit lower than that. That'd be one way that I could use logic to figure that out. The other thing I could do is literally get a decimal for it. Remember how we had these decimal values over here that we talked about? You could take pi as 3.14 and divide it by 6, and that would give you 0.52. So if you were asked to graph 0.52, hey, I know that this is 0 and I know this is 1.57. So if this is 0 and this is 1.57, 0.52 would be kind of like a third of the way up, right? Now this is getting a little bit ahead of ourselves because we'll look at this for the second half of this lesson. But if pi is the same thing as 180, that would just be 180 divided by 6. That'd be 30 degrees. So that'll give me another way that I'll be able to utilize if I can know its degree equivalent. Okay. Now, we said that it wouldn't matter which one of those you graphed, you would get the same initial side and terminal side. Let me prove that to you. There's the graph of 1 pi over 6. What if we had graphed 13 pi over 6? Well, 13 pi over 6 means go all the way around, that's 12 pi over 6, and then go one more to get 13 pi over 6. Same starting point and stopping point. How about 25 pi over 6? Well, 25 pi over 6 says start right here and go all the way around. That's 12 pi over 6. Go all the way around again. That's another 12 pi over 6. So that'd be 24 pi over 6. And then that would leave me one left to get to 25 pi over 6. So they would all have the same starting point and stopping point, whichever one I graph. I definitely want to choose the easiest one to do there. Okay? All right. Last thing we want to talk about today is the idea of complementary and supplementary angles on the top of page 287. All right, you'll remember from geometry in your geometry toolbox that complementary angles are two positive angles whose sum is 90, and supplementary angles are two positive angles whose sum is 180. So let's move that from degrees to radians. If 90 degrees is pi over 2 in radians, then I could say that complementary angles are two positive angles who have a sum of pi over 2. And if 180 is the same thing as pi, then I could say supplementary angles are two positive angles whose sum is pi. So let's start with degrees, and we could use the pattern that we know how to do with degrees to help us figure out what to do with radians. All right? If I asked you to find the complement of 50 degrees, what would you do? 90 minus 50, right. So you would take 90 and subtract the angle you were given. So let's do that same thing over here. What's the equivalent of 90 in radians? Pi over 2. So we're just going to take pi over 2 and subtract the angle we were given. One more time. If over here, to find the complement, you do 90 minus the angle that you're given, then over here, I'm just going to use the radian equivalent of that pi over 2, and I'm going to say pi over 2 minus the angle that I'm given. All right? So once I get it set up, it's just working with fractions. We're good with that. It's the setup that we want to make sure that we've got. So I need a common denominator for 2 and 5. That would be 10. So we'll rewrite each of those fractions with a denominator of 10. And then we could subtract to get our complement. All right, what if I asked you to find the supplement of 50 degrees? What would you do? All right. Awesome. All right, I would do 180 minus my angle. So we're going to copy that same pattern over here like Matthew said. The equivalent of 180 is pi. So we're just going to do pi minus our angle. So one more time, if over here you would have done 180 minus the given angle, then over here you're going to do the equivalent of 180 pi minus the given angle. And again, I just need a common denominator to subtract. Now, one thing they stress to me is that these have to be positive angles. Like, if I asked you to find the complement of 100, you can't find the complement of 100. It's already too big, right? It's already past 90 degrees. So there's not one because it's greater than 90. If I had used my handy-dandy little formula of 90 minus the angle that was given, I would have gotten a negative answer, and that would have been contradictory to the definition. I'm not as familiar with radians, so I might not recognize when they ask me to find the complement of 2 pi over 3 that that's already too big. But if I use my formula and I get a negative answer, that's how I'll know that it was too big, because it has to be positive.